Okay, there's ominous silence. So we'll have the second lecture from Vincent.
Thanks. Okay, so please let me know if you don't hear in the back. Or so today I'll try to discuss a problem in the context of the cerebellum that I explained last time. And the problem is a credit assignment in the sense that how each neuron knows it should be modified in the context of a complex task. Okay, so I'll try to explain that. Next slide. Before that, in the first lecture, somebody asked about the glial cell in the cerebellum, and actually I was not very good in answering that. So I'll show you just this, just to answer this question. So, of course, there are glial cells in the cerebellum, but also there are very... This one doesn't seem to work. Okay, in any case, there are very spectacular... So they are very spectacular glial cells. So these are these Bergman glia that are... so there are 8 Bergman glia for each Purkinje cell. And people are speculating what they can do. One thing they can do is that they certainly regulate the potassium homeostasis, meaning the acceptability of the whole system. But they also have AMPA receptor, and so they may have many other roles. So in fact, they play a very important role in the development of the cerebellum. I mean, they are radial glia that organize the development. So you have a nice review, probably a bit, oops. So, okay, do you have another point now? What? Okay, so there's a nice review by Jose Oakland, and the picture was taken from Morrison. Okay, so I'll go to the main topic of the lecture, the main topic that I want to discuss. So if you think of a complex task like bike riding, it's a complex movement, and there are many subtasks, many muscles involved. And the error that you get is actually very poorly informative. Basically, what you obtain is that, okay, either you fall or you don't fall. So you have some global errors from the proprioceptive system, but it doesn't tell you, in substance, which muscle should be more contracted, what you should do to avoid falling. And in many cases, even the sign of the error in this kind of complex task is not known. I mean, it's not known if you have contracted enough this particular muscle or not contracted enough. So the question is how the brain, and in particular in the case of complex movement, the cerebellum is going to do that. So this particular problem was called the credit assignment problem by Minsky, I think, in his PhD physics. So that's, of course, in machine learning, this is avoided because you can compute exactly the breakdown, so you know what's the influence of each unit on the performance of the loss function, if you want. But in the context of the brain, it's very difficult to imagine that each neuron knows, as a way of knowing, if it fires less or more, what would be the influence on the task. So that's a very, actually, difficult problem. And a solution that has been around for long is to go by trial and error. So the idea is it's a form of stochastic gradient descent with the name, for those of you who are machine learning aficionados, is a bit different from what is used. I mean, in machine learning, what stochastic gradient descent means that you have only a finite batch of examples that you go batch by batch. Here, what I mean by stochastic gradient descent is just that you perturb one unit or maybe several units stochastically, and then you look at the performance of the task. If the task is improved, and say you have, say, this unit has fired a bit more than they do usually, and the task is improved, then you would do potentiation of their excitatory synapse because you have gone in the right direction. Okay? So the idea that has been proposed is to perturb some neurons, see if the influence is good or not, and then do potentiation like this. And this is the kind of thing I want to discuss today in the context of the cerebellum, to see if we can implement this kind of learning. And this has previously has been considered mostly in the context of learning song in birds. So that's what we try to remind you of. So the outline of what I want to, yes?
Is it possible to learn which elements you should prefer moving the curve? Maybe there's a couple that you have learned over past experience that are more useful.
Maybe, but okay, maybe it's possible. It has not been certainly developed. But, yeah. So one thing that will, and maybe is clear from the beginning, is that this suffer from being a bit slow. So any idea of how to improve that is certainly welcome. So yeah. So what I just like to do today is to remind you a little bit what people have done for learning song in birds, what they have proposed, like that, shortly. Then I will try to describe you a proposal for the cerebellum, which is a bit different from the usual classic view that I described last time, and some experimental results, how this can be implemented. I mean, and at the end, I will tell you a little bit some recent experiment, the results. Okay, so let's start from song learning in birds. So what people usually study are zebrafinch that are easy to raise. And so this songbird, they learn their song by hearing the song of a tutor and repeating it. So, and the song gradually improves as the bird vocalizes. Even if the bird is isolated from its tutor, it can still continue to sing and improve the song. So the bird has some memory of the tutor's song and try to improve. And if the bird is deafened during the vocalization period, meaning it cannot hear what it is singing, the song does not improve. So it has to, in some sense, compare the song that it produces to the song that it has memorized to improve. And so a long time ago, Kenji Doya and Teresenovsky proposed that this is done by this trial and error in this trial and error way. And the idea is that there is this area element, which is here. So here there is the part that shows you the song. So this would be in some sense like a broadcast area for them. So this is the production part, and here there is a perturbation on this array, and that the bird uses this perturbation to improve its song. And so this part, I mean, there are many experiments that go in the favor of this. They also, so in this kind of framework, one should compare the perturbed movement or song here to some current performance, so one should evaluate the perturbed song, and they propose that this is done in this area X, and at the moment I don't think there is a very good evidence for this. This is rather unclear. Okay, so this was proposed a long time ago. This was implemented, so the way it was first proposed is that there were synapses that were grow or retract, and then Ilya Fichte and Sebastian Song and Michael Fee proposed that this area directly perturbed, Hellman directly perturbed the era RA, and so that's what they developed a model where they could implement that. So here, the idea is that so here they really put the error by hand. So they compare the song that is produced to the model song that you want. So there is an error term that you compare to some baseline threshold, and then you adapt. So if the performance is good when you have performed, you potentiate the synapse, so you improve. See, if when you are perturbed, you have increased the firing rate, this is a good perturbation, you increase the synapse, and otherwise you depress it. And with this kind of algorithm, they could show that, in fact, they learn quite well. So this is like the tutor song, this is before and then after. So here you have like a pattern generator, and here what this layer does is both to increase the amplitude and the frequency of this local frequency of this firing. Okay. So the question is, so even for this song learning, there are many parts that are missing. Where is the song evaluated, etc. So what we like to do is to go back to the cerebellum and try to see if we can propose some implementation of this stochastic gradient descent and see what would be the experimental implication of this proposal. Okay, so I just remind you shortly to contrast with what will follow, what the classic view is, which I described before. So the classic view is that, okay, you have this this MOSI fiber that acts on this projection neuron in the deep cerebellar nucleus, and you have some, suppose you want to achieve some motor task, somehow the ODE is supposed to know what you have to do, what the task, how the task will be achieved, and so it will send an error signal to this working SL, and this will change the plasticity of this, will change the firing of this working SL by modifying the synapse here between the MOSI fiber, the parallel fiber, and the working SL. So changing this synapse. So the question in this framework is how, in some sense, this cell knows that this Purkinje cell is responsible for the error. Yes?
Maybe you're going to talk about this later, but I was curious about this inferior olive error signal.
Yes.
And also from the prior slide to the Songbird circuit, there's a difference term that's computed there.
Yes.
And I was curious whether or not that's taken as like a assumed signal, or if you have thoughts about that. That to me is one of the more mysterious aspects of all these models. I've basically only seen like a handful of circuits in the brain that very clearly compute that. So I was curious about kind of the origin of that upstream error signal, both here and in the prior
slide. So think of a classical task like, say, VOR. So you would have the image would slip on the retina. And so that would be the error signal. If you think of the other types that I described, that is idling conditioning, where you remember you have a light, so conditioned stimulus that predict a puff of air on the eye. So there again, the error is just that you receive air on your eye without having closing it.
I guess I'm interested in the circuit that maybe this is actually offline, but like the circuit mechanisms that are proposed for that.
So there is a purely sensory input that will target the olive. If you think, say, of puff of air on your eye, this is just sensory that will target the olive.
With the Songbird case, that's less clear, right? Because how you have a complex song that you produce and you listen to, and then many features to it.
So if you think, so in reality, nobody knows how it's done. In the case of the model of Lafitte and Sebastian Song, what they do is that they chop this song in small pieces, and they just compare this to the real song, and they send an error signal. So it's just by hand, if you like. You just compare small time step by small time step the song to the tutor song. If it's, and this is your performance.
Point by subtracted, or do you they compute like filters of it and then like
Oops, sorry. So here what they do is that they compare, say, in these two things, and okay, they sum the error in pitch and amplitude, so amplitude or pitch, and this is the error that is computed for this time step. This is what you do. And so when you have the perturbed song on this precise thing, so precise time element, you ask, is it better if I have increased the firing of some neuron, or is it worse? And if it's better, then you potentiate the synapse of this. But you're right that in principle, I mean, here, it's actually very not obvious how this olive cell can know that it should, I mean, this olive cell target this Purkinje cell, but why the error is, how the error is specially targeted to this olive cell is not clear at all.
Vincent?
Yes.
Can you just repeat again what you were saying before the questions, like how the learning works in this network? Just repeat what you were saying before the question.
How here?
Yeah.
Here, okay, so here what you have is that you have an error signal that comes from the olive. You have a context signal that comes from the MOSI fibers. And so if you have an error signal that comes, it will, so it comes, let's say, 100 milliseconds after this context signal. When you pair these two, you depress this synapse. Okay, so I'll show you
So it
the...
has to be timed
Absolutely.
kind of precisely.
Absolutely, so this, I'll show you the...
And the green nucleus is not involved.
Okay, the green nucleus is the output, so this is the deep cerebellar nucleus, so this Purkinje cell will target this green nucleus, and this green nucleus, in fact, what this will do and modify the output of this green nucleus. So if you think of, say, VOR, where you turn the head and the eye has to turn, is by modifying the output here, it will change the gain of what the eye is doing. So the basic idea is that you change this and this will change. Okay. So, and as I was saying last time, and I remind you, these two things, if you induce spike in the Purkinje cell via the parallel fiber, this is one type of spike that you can recognize in electrophysiological recording, and the spikes that are induced by the excitatory input from the olive have a different shape. They are called complex spikes, so you can distinguish the two. Okay. And so the basic, so that's what Rava was asking about. So the basic plasticity, if you are in slice, is that you have this parallel fiber, and then the climbing fiber, say with 150 milliseconds after. And if you pair the two, if you have a signal from the parallel fiber, at first it will give a big signal, and if after this pairing, it will be smaller. Okay, so you have the depression of this. Okay. And it is supposed that there is a compensatory potentiation of this synapse if there is no climbing fiber signal on a longer time. Okay. Okay, so what are the questions one can ask about this theory? So first of all, error in this case lead always to synaptic depression. So this is so it means that error in some sense always comes from too strong synapse, which is a bit strange. In simple task, as I was saying, the sign of the error is rather obvious. I mean, you have the slit on the image on the retina is one sign or the other, or if you receive the buffer, it's clear that you should close your eye. So the sign is clear, but if you have a complex task with many subjects, the sign is not at all clear. And of course, the main thing is, even a complex task, how does the brain determine the precise source of it? So that's what we want to tackle.
Questions?
Yes?
There is one question on the...
Sure.
Why do you need you said the last point was precise, the precise source of error? I thought that the model just give the error signal to all the...
To what? Well, you want if you want to achieve, say, a good movement, say, cycle, you want to know if the error is coming because you have not contracted enough your arm, or because your, I don't know, your ankle was not at the right place. So you need to I mean, if you want to get the right movement, you should correct at the right place. You cannot correct somewhere else. No. Yeah. So that's just what I meant, I mean, nothing fancy.
Another question.
Yes?
So if there is only synaptic depression,
So there is, I mean, in this Mar-Lucito theory, the idea is that coincidence of the error, the error should lead to depression. The idea is this climbing fiber is signaling error, and climbing fiber is depressing the synapse of the Purkinje cell with the parallel fiber. Okay, so.
but how do you connect different directions of the error? Do you want to follow the bigger scale?
So the idea is that if you don't have the error signal, you'll potentiate less precisely.
Globally.
So you have a kind of a global potentiation and depression. Okay, so that's the way. Okay. And in fact, in the case, this is something that I did not have time to describe last time. I wanted to do it, but there are precise models that actually work in this case, because there the sign is here. You have rather simple model. Okay. Okay, so what are the questions that we would like to answer? So first of all, if we want to do this perturbation, we have to propose something like L-man for the bird song that perturb the movement. Okay, so what's the source of this perturbation? Then we'd like to answer or to propose a place, I mean, anatomical structure that would store the current performance. And then, if this is, we have an algorithm, then we can try to study it and see how it works. Okay, and also if there are specific predictions. Okay, so let's see. So the idea, I mean, the idea for the perturbation is that maybe the signal for the olive is not only an error signal, but maybe it's also a perturbation signal. So the idea is that the olive, if you record from it, these olive cells are active at 1 Hz, rather stochastic. So the first proposal is that this olive cell may induce perturbation all the time. Okay, so that's the first thing. So what would be the consequence of that? So this is the usual, the usual thing. You depress when you pair, but here, if you are in this framework and you want to, so the idea to use this perturbation is that you tag some neurons that have been perturbed, and these are the neurons you want to modify. Okay? So this has a direct consequence for the plasticity rule. You want to say, okay, first of all, I have input that I perturb, so I need this complex spike from the climbing fiber. If this is good, I won't have any error, so I will potentiate. If on the contrary, I have perturbed, so I've increased the firing, and it's bad, I will depress the synapse with the parallel fiber, okay? So it makes sense, I mean, it's just repeating what I've said before. And of course, in this case, if you don't have signal from the climbing fiber, even if you have an error after one, meaning you have a signal, since it's a cell you have not perturbed, you should not touch it. Okay? So you see that it's a sometimes very different prediction, because here I have LTD, here I have only LTP, so here I have this prediction with 2 complex spikes. And it's also a bit, say, bad in some sense because this has been seen in many experiments. So the only way this could not hold is if the condition of the experiment were not appropriate. So what was done, I will show you the experimental result just after, but to change this, the idea is that here the calcium is a bit high usually, so that all these plasticity rules depend on calcium. So the idea is that here maybe the calcium was a bit high, usually inhibition is blocked in this experiment, so Boris Barbour and collaborators decided to redo this experiment with lower calcium, weaker stimulation of the granule cell, and not blocking inhibition, all things that would diminish the calcium in this calcium entry in the Purkinje cell. And if you do that, in fact, you see what you hope for. In some sense, this is what you have here. So these are plasticity experiments where in slices where you repeat pairing of some granule cell input to the Purkinje cell with climbing fiber input with a delay, it's I think 150 millisecond interval here. And so if you repeat that, you have very few change. If you repeat, you pair the input from the palette fiber with the climbing fiber, you potentiate. And on the contrary, if you go with, it's here 100 milliseconds, if you pair this with 100 milliseconds, then before and after, you see a depression. Okay? So here there are two pulses because you have pulse facilitation, that the black is before pairing and the color is after.
But the difference between the green and the purple condition is that you have.
So here, this one you don't have the perturbation, you just have the error. So that's the usual protocol. But here you don't see anything because you have changed a bit the experimental condition. And basically you don't see anything. So I mean, the idea is that as for pyramidal cell, the idea is that at the synapse, if you are above the first threshold, you depress for calcium. Above the second threshold, you potentiate. In the cerebellum, the thing is inverted. So if you are above the first threshold of calcium, you potentiate, and above the second higher, you depress. So the idea is that by changing the level of calcium, maybe you could change the rule, and this is in fact what you see. Okay, so that's the first thing.
But there's also something of this kind happening because in the purple case, the first perturbation changes the level of calcium, and that's why you get depression with the pairing with the second one?
No, here it's sometimes you have a lot of calcium entry.
Because of the first?
Because of the two here.
Two here.
And the one that is coincident here. So you have, the idea is that you have a lot of calcium. Okay, so basically this is what it was. So you have you have depression when you have this pairing, if this is an error and this is a perturbation, and if you have only a perturbation and no error, you potentiate. And so this was done at TNS by Boris Barbour, and this is in replicated by another group, actually. So there are at least two papers that find the same.
You call it perturbation just because they're injecting some...
I'm calling it perturbation, but because I want to interpret it as a perturbation in behavior.
But why couldn't it be also an error? It just happened to
It could be anything. The idea is that the idea is that, okay, we're proposing that this is perturbing the
Oh, I
movement,
see, it's randomly coming, okay, fine.
and now we have this experimental sizes where you put this as a perturbation predictor. Okay, so now the other question is how are we going to, how could the current level, current performance level be stored? And the idea is that, okay, this is stored in a comparison, so I have added a piece of the circuit that I didn't put in the previous slide because it was not used. So the idea is that when this MOSI fiber arrive, they not only target the projection neuron that give the motor output, but they also target a part of the deep cerebellar nucleus that go back to the olive. And in fact, that inhibits it. Okay? So the idea is that basically the performance would be a comparison between the inhibition of the olive that is given here and the error. Yes?
Sorry, what exactly is the NOI here?
Nuclear, it means nuclear olivary neurons, which means that, which are neurons in the deep cerebellar nuclei that target the olive. Okay? And so these are well documented in people. So the idea is that, okay, you have some current inhibition on the olive, and if you want to have an error, it means that it should be big, the olive should fire, so it means that the excitation should be bigger than the inhibition. Okay, so the idea will be that the level of inhibition in this, on the olive will be the current level of your performance in some sense. So if your error is smaller then usually you won't fire anything. If the error is bigger, you will fire. Okay? So now the plasticity side. So of course, in the case of the bird song, they adapt, they have something like that, but they adapt the threshold by hand. And so now the question is, you have to, of course, you want to track your performance as your learning progresses, so you need plasticity of this inhibition. So you could have plasticity here or here. And so since plasticity has been described on the MOSI fiber, on the projection neuron, we propose that the plasticity is taking place here, meaning the synapse of the MOSI fiber on the nuclear olivary neuron, and that's what we use afterwards. Okay? Okay, so I gave you the anatomical substrate. Now I'll go to a fully stylized version. So what do I want to do in some sense? So I have like a collection of Purkinje cells. I will say, okay, each one wants to have a firing rate, target firing rate. And what I measure is not the individual firing rate of these cells, but say the sum of the deviation, okay? So the global error. And as I said, I have an internal estimate for this. This I just I estimate. And now what I want to do is to bring these to their value. Okay. So what I will do, I will choose randomly one of these cells, and I will perturb it by some quantity A. This will give me a new error that I will compare to my estimated value of the error. So if this is bigger than my estimated value of the error, so remember I is for inhibition, so I compare the two. If this is bigger, I will fire an error, so this is not good. It was not a good idea to increase this. So I will decrease my firing rate of this particular cell, because this is the one I've perturbed, and I will also refine my estimate of the error. If it was good to increase the rate, meaning that this EP is better than my current estimate, then I diminish this firing rate, and I also increase this firing rate because I've perturbed it and I diminish the error. Yes.
So, so there is EP and then there is I.
Yes.
So I is estimated value.
So I is the current inhibition on, it's the estimated value of my performance is E, if you like.
But
not perturbed.
But what is the connection between EP and I? Because you say the EP is estimated value.
Okay, so I have a current error.
Yeah.
Okay, now I perturb a cell. So my error changes.
What error? I.
No, EP. The error, the definition, okay, let's go back. Sorry for that. The definition of the error is just I have a collection of cells, I have target firing rate.
IP is the part of error and you call it I.
No.
No?
I is my, so what the error I'm doing in behavior, if you like, is this. Okay? If I was perfect, all perfect cells will be on their target, I would do this perfectly. I have a fantastic drive.
So that's the behavioral error.
Okay? But this, I don't know. What I have, some estimate of what I'm doing. Okay? Now I'm doing something, and is it better or less good than what I'm doing usually? Okay? So I have an estimate of this. I do a perturb movement. You only have perturb, I think. So I have a perturb movement.
But then you can observe EP, no? EP is observable.
EP, I observe.
Okay.
Yeah. I mean, for example, I don't know, play golf.
Okay.
You're much better. Okay.
Okay.
So if it is better, then actually this was a good idea. Okay, in some sense, that move P closer to my target.
So EP better means that EP goes down.
It goes down, yeah, the error goes down.
Okay.
Yeah, maybe that's confusing. E is the error,
Okay.
so it goes down. And then, okay, so
And then what is I?
I is the current estimate of the error. Current estimate of E.
Your internal, you encoded the estimate of what the error was.
Yeah.
When you carry that.
Your current performance. Okay.
But there is, I understood that EP is the performance. Oh, sorry,
E. So there is a real performance, but this you just estimate it. In your, I mean, you have some synapse.
And you call it E.
Yes.
Okay.
This is inhibition. Inhibition on the olive.
But,
I want to store this value, but I just have to estimate this value that I store, so I have to estimate.
So I is some value that your brain has encoded somehow and is an estimate of its performance, but my question is that EP is something that you read out from behavior.
Exactly.
So you have to behave again and again for each neuron.
Of course, if you like to learn to walk, you have to. So, but that's an issue. You're perfectly right. And the question now is this will be slow. Okay, that's perfectly. Okay, so actually, the way I've described it, if you try to, I've done it for 5 cells, but actually it doesn't converge, simply because the way I've written it, there is a conserved quantity here. that the sum of the error and the firing rate are conserved because I increase. So the way to go around this is to say that, okay, there are two kinds of moves. You have the move I've described where perturbing, but also other moves where nothing is perturbed. I just adjust the error. Okay, so I refine my estimate. Okay, so that's two kinds of move. One where it's perturbed and one where it's not perturbed. Okay, so now if you do that, say in this 5-cell case, you have your error that goes down and you converge. Okay? And the other one, they go to their target value. And you could do that for many moves.
But how do you improve your estimates magically?
No, it's not magic. Each time I am, so if the, so I'm updating my estimate, okay? So if perturbation was good, I increase the 500%, but I also decrease my inhibition, and I do the other thing. So I improve the performance, but also improve the estimate. So I'll show you how it works in a very simple case. So if you, so this would be with several cells. So there are 3 successive phases in this learning process. In the first, so you have the black is E, what your performance, and the red is your estimated error, your I. So at first, the two are very different. I mean, there's no reason to be the same. So in the first phase, what actually you perturb the movement, it doesn't improve, actually it deteriorates. But what you gain in this first phase is that your estimated error coincides more or less with your real performance. Then when you have a good estimate of the error, then both go down together. And at the end, so, okay. So you can look at it, so in the one cell case, it's quite easy to see it. So you would have 2 types of trial. So either you perturb or you don't perturb, and each time you change the error or not. And so the way you proceed, you can, it's the same thing for one cell, very easy to do. And then you can try to see, to plot what you have here. So if you look in this I firing rate plane, so you have 2 variables, your estimate of the error and your firing rate. So what you will do is that, okay, there are 2 lines depending on if you do a perturbation or no perturbation. And basically what you do is you have a point somewhere else and you follow these lines. So you go here and then you basically you go down this corridor towards the so I can show you a little bit. So basically this is a phase plane analysis, rather simple for just one. Okay, and so even this, so basically these are trajectories in this firing rate estimated error plane, and so basically you go down, and so this is the place where you refine your estimate, and then everything goes down, and depending on the, so there are several parameters, what is the frequency which should you perturb or not, and what are the size of the perturbation, and also your steps in refining your error and changing the firing rate of your cell. So you have 4 parameters in this case, and depending on the parameter, you can either go down along one of these lines or the other. Okay? And you can basically compute how you go down in this, you converge to your desired solution. So this is for one cell. So you can also do it, so this was very stylized, but in fact very similar if you replace all these, so here I only track the firing rate, so you can in fact replace all of these by analog perceptron. So here what you have this input from the granule cell, so here, and you have some threshold, and here I put this rectifying linear unit that people love in the machine learning community, but it's just saying that, okay, it's linear above a threshold, okay, and you want this P, this output, to be some target rate. And again, so you can, and you have the same thing on the DCN, so each, you want to learn input, so there are some so what you want to associate is to some input here, some output there, and a few of them, so you can do that. And again, you would have exactly the same plasticity rule as before. I mean, you would perturb this perturbing cell output with some value A and some, and it's for some of the trial with a probability rule.
So this E is the output to the nucleus, the DCN?
So, sorry. So basically, yes, so P is just the output of the Purkinje cell, which in fact will go to the DCN. But in this, at this stage, we just keep track of the output of the Purkinje cell. But you're right that on the movement, their influence on the movement would be through the DCN.
E equals E minus I, what is it?
Okay. So here you have again, so this will be, actually should be, in some sense, this should be reversed. This would be what will go to the DCN, and this would be this is the error, and this is the inhibition coming from this pattern. So you have to, so if the error is bigger than this inhibition, you will fire, another one you won't. So this is exactly the same as but here the inhibition is specific to the pattern. Here we're going to consider that we don't learn only one, so we consider only one Purkinje cell, but we have several patterns, and so each pattern will have its own estimate of the error. Okay, because this input is also targeting the DCN. So this is simply that there is a specific error for each pattern.
The normal perturbation is just that I relaxes to E.
Exactly.
Essentially, it's just a relaxation of I.
Exactly. Okay, so that's basically, okay, so, and basically if you do it with a perceptron, you see very similar things, and you can learn actually basically up to the maximal capacity of this perceptron with this algorithm. But if you look, what you have here is that it would be the usual delta rule, and if you do real gradient descent, basically you have 100 steps, and here you have 10 times more. So in some sense you are learning this, all this is converging, but this is slow. So this is somebody suggested that there could be some improvements. Yes, certainly it would be nice to have some improvement. Okay, you can do with N cell, as I was saying, and you can do the same kind of analysis for N cell and see that you can converge. Okay, so yes.
One question about improvement. So to connect with what Nathaniel was talking about, for example, here you just have an error and you want to decrease it, but you have no model of how you produce that error. If you could also learn a model of how you produce error and then kind of simulate and use that instead of having to behave every single time.
This is possible, but I think learning the model will be, I mean, sometimes you have to learn this model too, so.
But from the same data.
Yeah.
But you would also learn.
I mean, here actually there is no real model of this data because it's a kind of random association. So what you're saying is that if I have many patterns, maybe, and that these patterns are produced by some model, then maybe it's more economical to learn the. Yes.
So I didn't mean to interrupt mid-sentence. I was going to say that it would be interesting to know, like people like Daniel Wolford and
Yes,
human motor control
of course.
think that cerebellum is involved in kind of forward modeling consequences of actions.
Of course, but you have to learn this model.
Sure, yeah, but
so that's, I mean, in some sense, we are a bit agnostic to that. In some sense, we are saying, okay, how in a model or in a direct movement, how do you learn that one cell is doing something? This is, you have the same question if you want to learn the model. But, okay, in the end, it's maybe useful to have a model. Okay, so what we have at the moment is we have this proposal, we have this this experiment in vitro that show that I mean the thing is conceivable that you have plasticity with two climbing fibers, complex and use complex fiber. But there are many, of course, things that should be seen in vivo. So there are ongoing experiments. One experiment that I think was nice, the first thing for this to make sense is that you need, what I said is you perturb the movement by this complex spike, and then you improve it. So the first thing that you need to show is that, in fact, if you have a complex spike during a movement, it will perturb the movement. This can be seen. So there is a recent experiment in Reza Shadmir lab that shows that. So the experiment is marmosets that have to fixate a saccade. So then, when the marmoset is doing the saccade, the target is moved. So after the saccade, there is an error because the eye is not on the target. So with this, displacing the target in many directions, you can see which are the directions that induce firing of the complex spikes. Okay? So with this, you can say, okay, this complex spike has a preferred angle. So it spikes actually not for all displaced targets, if you record one protein cell, but it has a preference. It will fire more if this error is in this direction. Okay? So there is a direction preference for the errors that are detected by the complex spike. Okay? And then what they looked at is that during this saccade, sometimes there is a complex spike that appears, and they try to see how it displays the saccade by itself. Okay? And so what they measure is that, in fact, yes, if there is a complex spike during the saccade, it actually displays the saccade in the particular angle that is preferred by the complex spike, the target in this curvature set. So here, if you have a complex spike during the saccade, it will displace the thing, and so the perturbation is rather small. It's 1% of the eye movement, but this is, and they show actually that if you, sometime in their recording, they have two Purkinje cells that are perturbed at the same time, and then that have the same preferred direction, and then they show that, okay, the perturbation is actually more than double. Okay, so that's the first thing. The second thing is that people that have recorded the olive, in fact, have seen that the olive is actually more complicated in some sense than just giving an error. So people tend to interpret this experiment in terms of reinforcement learning. So what here, this is idling conditioning. This is data from Javier Medina's lab. So what you see, so you remember in idling conditioning, you would say some signal and the puff of air, and what happens is that before you close your, this is eyelid closure, so you close your eyelid after the puff. After conditioning, you close your eyelid before the puff, but what is seen is actually in the complex. So what you see is that this complex spike tend to disappear afterwards, so there are less error. But what is was discovered in this paper is that actually you have a lot of complex spikes that have appeared tied to the lead motion. Okay, so now you have anticipatory complex spike. So the dynamics of the olive is more complex, and they tend to show that even if they omit the puff, then you have less complex spike afterward. And so this has been also seen in operant conditioning tasks, where the mouse has to press a lever, except that the sign is not exactly the same here. So it says in any case that what is happening in the olive is more complex than just error emission. And okay, so the question is if some of this spike can be used, in fact, for as an increased perturbation is not there. Okay, so that's basically the story I wanted to tell you. So just to summarize, so the classic theory of the cerebellum is faced by this credit assignment problem. We propose the trial and error perturbation. So there is some evidence in plasticity rule. The in vivo situation is less clear. And last point is that actually the fact that you perturb and use the perturbation to go in one direction or the other may be used in other structure. So one can wonder about that, and maybe actually the basal ganglia would be one possibility, because there dopamine is has really a dual role. One is really to choose, it's thought to have a dual role. One is action selection, and then there is this reward. So are there plasticity rules that involve both signals? This is the question. Okay, and last is people. So this experiment that I showed on plasticity was done by Guy Bouvier in the lab of Boris Warburg. There is a bunch of theory people who have discussed that, and there are current in vivo experiments in Boris' lab and also in Stefan Dieudonné lab at TNS, where we see all kind of things in the olive that are not so easy to interpret. Okay, thank you.
Let's have a couple of questions.
From what I know from previous experiments, it seems like even in well-trained animals, you still get complex spike signals. And we usually take that to be in conflict with the idea that it's denoting some kind of error, right? So how would you interpret that in your framework? Like, are those perturbations that?
So the fact that there are errors, we also take, in fact, because you have this, to have this perturbation, we say that you need an error. I mean, the firing of the complex spike, say 150 milliseconds after the simple spikes that have been induced by the viral fiber. The question is, do you need before what to have introduced like this perturbation complex spike? That's the question. And so at the moment there are very few experiments that look in the course of training. I mean, most experiments, as you say, are in well-trained animals. So the experiment at ENS at the moment are just doing that and trying to see what is happening with the complex spikes in the course of learning and how do they evolve.
So is it true that your model also doesn't explain why you have complex spikes even in well-trained animals?
No, I mean, we don't, the fact that we have complex spike, if you have error, we just keep. The fact is that we don't, the point here is that we don't say the complex spike is completely instructed. In the usual model, what you say is that, okay, the complex spike will tell exactly this blocking cell should decrease its firing rate. What here we say, okay, in some sense the error is more global, but what you use to adapt your firing rate is the fact that you were perturbed before. Is it okay?
I want to interpret. She's saying that after training, the animal has no errors behavior, yet there are still complex spikes.
Yeah.
What is your theory?
I mean, you mean, so it depends. I mean, if you look at something like idling conditioning, clearly you have decreased a lot the complex spike during the birth. If you look at other behavior, sometimes you have actually, yes, what you decrease are complex spike before the behavior. We don't know exactly why.
Okay, so let's maybe take 5 minutes, if that's okay.
I think we can take maybe 10 to 15 minutes. And we have the life science discussion for half an hour. And then at 5 o'clock, we will have the students' presentation from 5 to